Welcome back. Problem 14-3. This problem is taken from chapter number 14, that is Energy Methods, and book name is Mechanics of Material by R.C. Hibbeler. So statement is determine the strain energy in the step rod assembly portion A, B is steel and BC is brass. Modulus of elasticity of brass is 101 gigapascal while steel is 200 gigapascal. Yield stress of brass is 410 megapascal and yield stress of steel is 250 megapascal. So you can see this is the step rod that is acted upon by axial loading at point C and B, and this is fixed at point A. The diameter is given for rod AB is 100 millimeter while BC is 75 millimeter. So we have been asked to find the strain energy in this step rod. Clear? So let's start with the solution. So first we will define what is strain energy. So again, you can see when you applied load on the body, clear, that will tend to deform this body. Provided no energy is lost in the material, the external work done by the load will be converted into the internal work, which is called strain energy. So basically the external workload is our work done on the body will be stored in the body as strain energy. This is what we call strain energy. Now you can see that this is axial loads, all are axial loads, and we know that, and this is step rods, this is one rod and this is second rod. So we can write strain energy, which is represented as UI for axial loading. Since this is axial loading, it is equal to sum of n square into L divided by 2 times AE. Clear? Where n is normal, our axial force, L is length, A is area of that rod, and E is modulus of elasticity. Now what we will do is that first step is that if we cut this step rod over here at section 1-1, let this is section 1-1. So at section 1-1, if I cut it and draw the free body diagram, so it will be like this. This is your point C, where you have 20 kilonewton load, and in order to keep it in equilibrium, you will be having reaction force opposite to that. Let this is NBC because this is rod BC. Now you can find this NBC by using equation of equilibrium, that sum of all forces in x direction must be equal to 0, and force toward right is taken as positive. So NBC is positive minus 20 kilonewton is equal to 0. So from here you will get NBC will be equal to 20 kilonewton. Okay, now what we will do is that we will take another section, which is section 2-2 in rod AB, and we will draw the free body diagram that is available on the right. So at section 2-2, draw the free body diagram. So this way there is a larger rod here and there is a smaller rod, which is rod BC here. So at this point you have 20 kilonewton here, which is your point C here. This is your point B, where you have 30 kilonewton, and here you will have also 30 kilonewton. So when you cut it, you will be having a reaction force. Now you can see 30 plus 30 is 60 in this direction, plus 20, which is 80. So in order to keep it in balance, this reaction force should be in this direction, and this will be NAB because this is in rod AB. So you can find this NAB by using this equation of equilibrium and taking this direction force positive. So NAB minus 30 minus 30 minus 20 is equal to 0. So NAB will be equal to 80 kilonewton. Now you have both normal or axial forces in this rod AB and BC. So what we will do is that we will use this equation. So strain energy due to axial loading is equal to sum of, so for rod AB it will be equal to NAB into length, NAB square into length AB divided by 2 times of area of AB into E. AB is made up of steel. You can see why this is made up of steel. So E of steel plus for brass or for rod BC, NBC square into length of BC divided by 2 times of area of BC, and this BC is made up of brass. Here it is given and this is made up of brass. So now you have all the values, so you can put it. So NA is, again NAB is 80 kilonewton. So 80 and kilo is 10 to the power 3 whole square. Length of AB is 1.5 meter. So I will write 1.5 divided by 2 multiplied by area. So you can see diameter is given 100 millimeter, which is 0.1 meter. So you can use pi by 4 into 0.1 square. There, and E of steel is also given as, you can see this is 200 gigapascal. So 200 into 10 to the power 9. Similarly, you can do it for N for rod BC. So NBC is 20 kilonewton. So 20 into 10 to the power 3 whole square. Length of BC is 0.5 divided by area, 2 times area of BC. So diameter is given as 75 millimeter, which is equal to 0.075 meter. So pi by 4 D square. So pi by 4 0.075 square into E of brass. So E of brass is 101 gigapascal. So 10 to the power 9. This will give you strain energy due to axial loading. So when you calculate it, you will get strain energy due to axial loading comes out to be 3.28 joules. So this amount of energy is stored in the body due to external work, but we will check it again. So this result is valid. This result will be valid only when your stress is less than the yield stress. So what we are going to do is that first we will find stress in AB, which is equal to NAB divided by area of AB. So NAB is 80 kilonewton, so 80 into 10 to the power 3, and area is pi by 4, 0.1 square. Here, and when you calculate it, you will get 10.19 into 10 to the power 6 Pascal, or you can see 10.19 megapascal. Now you can see that stress in AB is less than yield stress of the steel. Here you can see AB is made up of steel, which is this one, 250 megapascal. So this 10.19 is less than megapascal, is less than 250 megapascal. So it means that this is okay. We will check it for BC. So sigma BC is equal to NBC divided by area of BC. So NBC was 20 kilonewton. So 20 into 10 to the power 3 divided by area. So pi by 4, 0.075 square. Okay. So again, when you calculate it, you will get stress in normal stress in BC, and that come out to be 4.527 into 10 to the power 6 Pascal. Or you can say 4.527 megapascal. And you can compare it, sigma BC and sigma yield of brass. So you can see this is BC 4.257, while each stress of brass is 410 megapascal. So you can see this is 4.527 megapascal is less than 410 megapascal. So it means that your strain energy is stored in this body is 3.28 joules. And that was all about this problem 14-3. I hope you have enjoyed this video and you have learned from it. Those who are new to my channel, then subscribe it and don't forget to press the bell icon so that you can get notification about my latest videos. Also share my videos with your friends and help me in growing my channel as well as they will learn from my videos. If you have any question, you can ask me in comment section. Thank you for watching and supporting me. Welcome back. Problem 14-4. This problem is taken from chapter number 14, Energy Methods, and book name is Mechanics of Material by R.C. Hibbeler. So statement is determine the torsional strain energy in A36 steel shaft. The shaft has a radius of 30 millimeter. So you can see this is the shaft that is acted upon by torque of 3 kilonewton and 4 kilonewton at various location. So this is 0.5 meter, 0.5 meter, and 0.5 meter. This end is fixed. So due to this torque, you have to find the torsional strain energy. So let's start with the solution. So we know that strain energy due to torque can be represented as UI due to torque or torsion will be equal to sum of T square into L divided by G 2 times G, where T star L is length, G is modulus of rigidity, and J is polar moment of inertia. And you can see that at various sections, the torque is changed. So in this section, the torque will be different, in this section, the torque will be different, and in this section, torque will be different. So we will take sum of all this strain energy due to this torque. Now we will name these points that this is point A, this is point B, this is point C, and this is point D. So what we will do is that first, when you will section it between this length AB and draw the free body diagram, so this shaft will be like this. Clear? This will be the axis. And you can see this is shaft AB, so there is no torque in shaft A, along the length of shaft AB. So torque TAB will be equal to 0. So I will write it TAB is equal to 0. Now when you cut it along the length BC and draw the free body diagram, so for BC, the shaft will be like this. If I draw it like this, so this is point A, this is let point B. And you can see that point B you have a counterclockwise torque. This is 3 kilonewton into meter, and this is the axis. So in order to balance it, we will have a clockwise torque, and this clockwise torque will be equal to TBC, and this TBC will be equal to 3 kilonewton, but that will be in clockwise direction. So net torque in portion BC is 3 kilonewton. Now the last thing is that when you section it at CD, in portion CD, and draw the free body diagram, so for CD, if I draw it again, clear, so this will be like this. Okay, so this is your point A, this is your point B, where you have a counterclockwise torque 3 kilonewton into meter. This is your point C, where you have a clockwise torque which is 4 kilonewton into meter, and this is the axis. So in section CD, the net torque will be 3, which is counterclockwise, plus 4, which is 3 minus 4 is minus 1. So there is a counterclockwise, that is, there is a clockwise torque. In order to balance it, we should give it counterclockwise to balance it, and this torque TCD will be equal to 1 kilonewton into meter, and opposite to the net effect of these two. This is 3 kilonewton and this is 4. So net is 1 kilonewton clockwise, and it should be counterclockwise. So TCD is this one. Now you have all these torques, so you can just put it in this formula. So UI due to torsion will be equal to TAB square into length of AB divided by, since the material is same and diameter is same, so GJ plus TBC square into length of BC divided by 2. Okay, there is a 2, so 2 times GJ plus TCD square into length CD divided by 2GJ. Now you can take 1 over 2G as common from this. 1 over 2G, J is common, and we can put the value TAB is 0 and length of AB is 0.5. So 0 square into 0.5 plus TBC is 3 kilonewton, so 3 into 10 to the power 3 whole square into length of BC. So BC is, again, you can see this is 0.5, so 0.5 plus TCD is 1 kilonewton, so 1 into 10 to the power 3 whole square into LCD is also 0.5 meter. Okay, this will give you strain energy due to torsion, and this energy will be stored in the material in the form of work done. Okay, so when you solve this, again, this whole term divided by 2 will give you 2.5 into 10 to the power 6 divided by G into J. Now G is modulus of rigidity, and it can be obtained from the book Mechanical Property at the end of book available for A36 steel. So again, you can see here that we have A36 steel, clear. So modulus of elasticity G is 75 gigapascal. So you can put this value, G is 75 gigapascal, which is equal to 75 into 10 to the power 9 pascal. And J is polar moment of inertia. For circular rod, it should be it must be equal to pi by 2 C power 4, where C is the radius, and you can see the radius is given as 0.03 meter. So pi by 2, 0.03 power 4. So you can just put these values in this. So 2.5 into 10 to the power 6 divided by 75 into 10 to the power 9 multiplied by pi by 2, 0.03 power 4. And when you solve this, you will get torsional strain energy, which comes out to be 26.2 Newton into meter, and we know that this Newton into meter is equal to joules. So 26.2 joule. So this is the strain energy due to torsion, or you can see torsional strain energy due to given loading, and this energy will be stored in the object. And that was all about this problem 14-4. I hope you have enjoyed this video. Those who are new to my channel, then subscribe it and don't forget to press the bell icon and share my videos with your friends and help me in growing my channel. If you have any question, you can ask me in comment section. Thank you for watching and supporting me. Welcome back. In this video, we are going to solve problem 14-5, and that is taken from chapter number 14, Energy Methods, and book name is Mechanics of Material by R.C. Hibbeler. So statement is using boards of the same material and cross-sectional area, two possible attachment for cylinder heads are shown. Compare the strain energy developed in each case, and then explain which design is better for resisting an axial shock or impact load. So you can see this is design A and this is design B, and this is a piston, clear, and this is a cylinder head. So this is one arrangement using 4 bolts of each length L1, and here you can see the cylinder head is held by this single bolt of L2 on each sides. Clear? So you have to find the strain energy in this case and in this case, and then we will compare which one is better. So let's start with the solution. So for case A, you can see due to this movement of this piston, there will be shock or axial load in this bolt, and again the bolt experience tensile stress or axial stress. So we know that strain energy due to axial load can be represented as UIA. Since this is for case A, so I will write A, and that is equal to n square L1 divided by 2AE. Since area and material, cross-sectional area and material is same, so I will write AE. N is the normal stress or normal force in this bolt, where L1 is the length of this bolt, which is L1. So this is the strain energy in case A. Now for case B, you can write the same equation. UI for case B will be equal to, here you can see this bolt will experience normal load or axial load. NA, the bolt will be in tension, so it will be equal to N square, and length over here is L2 for case 2. A, 2 times A into E. So this is the strain energy for the case B. These are the answer of our first part. Now in second part, we have to explain which design is better. So explanation is that I will write it. So you can see UI for B is greater than UI for A case. Why? Because here length is increased. All other factors are same, but length is increased in case B. Therefore UI for B is greater than UI A, strain energy in case A. The reason I will also write L2 is greater than L1. So the design case B is better able to absorb energy. So our answer is case B is better choice. And this was all about this problem 14-5. I hope you have enjoyed this video and you have learned from it. Those who are new to my channel, then subscribe it and don't forget to press the bell icon. So welcome back. Problem 14-6. This problem is taken from chapter number 14, Energy Methods, and book name is Mechanics of Material by R.C. Hibbeler. So statement is, if P is 60 kN, determine the total strain energy stored in the truss. Each member has cross-sectional area of 2.5 into 10 power 3 square millimeter and is made of A36 steel. So you can see this is the truss that is made up of different member A, B, B, C, C, D, and AD. And each having area is this one. So you can see the area of each member is shown in meter. It is this one. Clear? And there is a load P which is equal to 60 kN. So due to this load, there will be axial stresses in this member. So you have to find the total strain energy stored in this truss. So what we will do is that first we will find the normal forces. So I will write it. So the normal forces can be obtained by using method of joint, by normal forces by method of joints. So we'll apply method of joint in order to find the forces in this method in this truss. So what we will do is that first we will take joint A. So you can see this is joint A. So due to this load, there will be tension in this member AB. As a result, member AB will exert force in this direction at point A. And due to this load, there will be extension in this member AD. As a result, this member AD will exert a force in this direction on this point. So we'll draw the free body diagram. So this is your point A. Clear? This is load P which is acting downward, and this is equal to 60 kilonewton. This member AB exert a force in upward direction. Clear? That is represented. Let this force is FAB, and the member AD will exert force in this direction at point A. Let this force is FAD. So by using equation of equilibrium, we will find this force. So first equation of equilibrium is that sum of all forces along x direction must be equal to 0, and force in this direction is taken as positive. So minus FAD, there is no other force is equal to 0. So it means that FAD, force in member AD, force member AD exert on point A is equal to 0. Now what we will do is that we will apply another equation of equilibrium, that sum of all forces along y direction must be equal to 0 and upward force is taken as positive. So FAB is upward, minus 60 kilonewton is downward. Their sum must be equal to 0. So FAB is equal to 60 kilonewton. Now this is the force that this member AB applies at point A. So as a result, due to Newton's third law, the force in this member AB is tensile. So we will write it. This force is tensile. Force in member AB. Now we will apply the same for joint B. So let me draw joint B. So you can see this is the joint B. Here I will draw the point joint B. So due to this load, this member AB will extend. So this member AB will exert force FAB in this direction at joint B, and this FCB will apply force in this direction. So I will draw it. So FCB is in this direction. This is FCB. Clear? And there is a FAB in downward direction. So FAB we have already calculated, that is 60 kilonewton. Clear? And this member, due to this, there will be compression in this. As a result, this member exert force at point B in this direction. Let this force is FCD. So FCD will be in this direction. This is FCD. Also, you can see the length 1.5 and 2. So here, if I draw the triangle, right angle triangle, so if I multiply 2 with both sides, multiply with this and this to get, this will be 4, this will be equal to 3, and this will be 5. So we'll get, I will draw the same triangle over here because it defines the ratio of the side. So this length is 4, this is 5, 3, and this is 5. Now we apply equation of equilibrium. So first equation of equilibrium is that sum of all forces along y direction must be equal to 0 and upward force is taken as positive. So you can see one force which is 60 kilonewton, that is downward, plus this force will have two components, one along x direction and one along y direction. So its vertical component will be equal to, if you take this FCD, and vertical component will be equal to FCD sine of theta, that this is theta, is equal to 0. So minus 60 plus FCD and sine of theta will be equal to 3 over 5 perpendicular over hypotenuse. So this is perpendicular and this is over hypotenuse. So 3 by 5. Their sum must be equal to 0. So again, when you solve this, you will get FCD will be equal to FBD, not FCD. This is FBD. This is FBD. So FBD, correct it as well. FBD is equal to 100 kilonewton. Now this FBD is the force exerted by this member FBD on point B. As a result, the load or force in this member BD is compressive in this direction. Clear? So I will write it here as compressive. Now we'll apply another equation of equilibrium that sum of all forces along x direction must be equal to 0 and force in this direction is taken as positive. So you can see FCB, which is negative. So minus FCB or FBC plus FBD cos of theta. This component FBD cos of theta. Their sum must be equal to 0. So minus FCB, this is FBD. Okay, plus FBD is 100 kilonewton, so 100, and cos of theta will be equal to 4 over 5 is equal to 0. So from here we will get this FBC is equal to 80 kilonewton. Now this is the force that member FBC exert on point B. Okay, as a result, force in member BC will be in this direction, so it will be in tension. So I will write it over here, tension. Now you have all the loads, so we will also we have the area which is given as 2.5 into 10 to the power minus 3 square meter. So the length over here BC is 2 meter, BA is 1.5. So you can calculate this length as well by using Pythagoras theorem, the length of BD, this length BD. Here, this is 1.5, this is 2 meters. So by using Pythagoras theorem, this will be 2.5 meter. So let me calculate it as well. Length of BD will be equal to under the root 2 square plus 1.5 square, and that will be equal to 2.5 meter. Now we will come towards our main solution. You know that strain energy due to axial loading is equal to m square L over 2AE. Since there are many members, this member is in axial load, this member bear axial load, this and this is 0 because this FAD is 0. So for many members, we will write sum of all these members. So I will 1 over 2AE. So we will take 2AE common. So n square in first member AB. We will take this member AB. So AB load is 60 kilonewton. So 60 multiplied by 10 to the power 3 multiplied by length of AB is 1.5 meter. So I will multiply it 1.5 plus this BC. This BC. So this BC having load 80 kilonewton. So 80 kilonewton into what will be the length of BC? So 2 meter. Clear? 80 into 10 to the power 3 multiplied by 2 meter plus this BD. So BD is having 100 kilonewton and length is 2.5 meter. So I will write 100 into 10 to the power 3 multiplied by 2.5. Now what will be the E for A36 steel? The modulus of elasticity. So we will get this from the property table, and you can see that you will use SI unit. So A36 is this one, and E will be equal to 200 gigapascal. 200 into 10 to the power 9 pascal. So write down E is equal to 200 gigapascal or 200 into 10 to the power 9 pascal. So put it in this value. So UI due to axial loading, strain energy stored in this truss will be equal to 1 over 2 multiplied by area is 2.5 into 10 to the power minus 3 multiplied by this thing 60 into 10 to the power 3 multiplied by 1.5 plus 80 into 10 to the power 3 multiplied by 2 plus 100 into 10 to the power 3 multiplied by 2.5. Now when you calculate it, you will get strain energy due to axial loading and truss comes out to be 43.2 joules. So that is the answer of this question. So what we are going to do is that we will check that whether this is valid. So this result will be valid. This result will be valid if your maximum stress will be less than sigma yield. So how you will find this maximum stress? So you can see maximum load between these. One is this one, the second one is this one, and third one is this one. So maximum load is this FAB. So we will calculate maximum load, which is equal to sigma BD, that is equal to 100 kilonewton. So 100 into 10 to the power 3 divided by area, and area is 2.5 into 10 to the power minus 3. So when you calculate it, it will be equal to 40 megapascal. Now for A36 steel, yield stress is, you can see yield stress is 250 megapascal. The unit is megapascal. So yield stress is equal to 250 megapascal for A36 steel. So you can see your maximum stress is less than yield stress. So your answer that strain energy stored in this truss is 43.2 joule. And that was all about this problem 14-6. I hope you have enjoyed this video and you have learned from it. Those who are new to my channel, then subscribe it and don't forget to press the bell icon so that you can get notification about my latest videos. If you have any question, you can ask me in comment section. Thank you for watching and supporting me. Welcome back. In this video, we are going to solve problem 14-7 that is taken from chapter number 14, Energy Methods, and book name is Mechanics of Material by R.C. Hibbeler. So statement is determine the maximum force P and the corresponding maximum total strain energy stored in the truss without causing any of the member to have permanent deformation. Each member has the cross-sectional area of 2.5 into 10 to the power 3 square millimeter and is made of steel, A36 steel. So you can see this is the truss there that is acted upon by load P. Each truss having cross-sectional area is this one. You can see I have written over here in meter, it will be 2.5 into 10 to the power 3 square millimeter. And there is a load P applied on it. So you have to find the P load without causing any member to permanently deform, and you have to determine the maximum total strain energy stored in truss without causing any member to be permanently deformed. So let's start with the solution. So first step is that we will find the normal forces in each member of truss. So how will you find this normal forces? By using method of joint. So we will take joint and then we will apply the equation of equilibrium in order to find this. So let's take the joint A. Joint A. So you can see here, this is joint A where P load is applied. Due to this P load, this member will be in tension. As a result, this member will exert a force which will be equal to FAB in this direction, and this member FAD will be also in tension. As a result, this member FAD will exert a force in this direction on point A. So we'll draw this. This is your point A. This is load P that is acting downward. Clear? This is your force FAB which is acting upward. Clear? And this is your force FAD which is acting over here. So first equation of equilibrium is that sum of all forces along x direction must be equal to 0, and force toward right side will be taken as positive. So one force is FAD which is in negative direction, and there is no other force. So it means that force applied by this member FAD on point A will be equal to 0. Now we will apply another equation of equilibrium that sum of all forces along y direction must be equal to 0, and upward force is taken as positive. So FAB which is acting upward minus P is equal to 0. So from here this FAB will be equal to P. Now you can see that this is the force this member AB acts on point A in this direction. As a result, force in member AB will be in this direction, which is tension. So I will write this force FAB will be in tension. Now what we will do is that we will use joint B. So I will use joint B. So you can see here, this is the joint B. Due to this load, clear, this member will elongate, causing this member will cause a force at point B in this direction. This will be FAB. Similarly, this FCB there will be an axial load in this direction. As a result, this FCB will exert force at point B in this direction, and this member will be in compression. As a result, this member will exert force FDB in this direction at point B. So we'll draw this V bar diagram over here. So this is your point B. At B we have FAB which is acting downward. So FAB is equal to P. Clear? Similarly, FCB will be in this direction, horizontal. FCB in this direction, and FBD will be in this direction. This FBD. Also, you can see this is 1.5, this is 2. So if I draw a right angle triangle over here, clear? So if I multiply this length with 2, it will be equal to 3, and this length with 2, it will be 4. So this is a basic triangle. Clear? And I will draw the same triangle over here. This is 3, this is 4, and this is 5. Let this force is making angle theta. So we'll find this forces by using equation of equilibrium. So what will be the equation of equilibrium? So equation of equilibrium, first equation of equilibrium is that sum of all forces along y direction must be equal to 0, and upward force is taken as positive. So FAB which is equal to P is acting downward. So P plus this force will have two components. One is this one, and other one is vertical. So vertical component will be equal to FBD sine of theta is equal to 0. So minus P plus FBD and sine of theta is 3 over 5. If you look into this triangle, is equal to 0. So from here we will get FBD into 3 over 5 is equal to P, and FBD is equal to 5P over 3, which is equal to 1.6667 times P. Now you can see this is the force that this member BD acts at point P, B. So the force in this member CB will be in tensile. So I will write T, tension. This will be in tension. Okay, this FBD. So we are talking about this one. So you can see that the force exerted by this member on point B is in this direction. As a result, force in this member will be compressive. So I will write it C. Now we'll apply another equation of equilibrium that sum of all forces along x direction must be equal to 0, and force in this direction is taken as positive. So minus FCB, clear, plus this component which is FBD cos of theta is equal to 0. So minus FCB plus FBD is 1.6667 times P, and cos of theta is equal to 4.5 is equal to 0. So from here you will get this FCB or BC will be equal to 1.333 times P. And this, you can see that this is the force that member FCB exert at point P. As a result, force in this member will be tensile. So I will write tension. Okay. Now we have all the axial forces in the member of the truss. So we will find the axial strain energy. So I will write axial strain energy. And we know that axial strain energy Ui due to A axial will equal to sum of n square L over 2AE, or you can also write it as sum of F square L over 2AE. Clear? And what we have is that we will use this formula, but before that we know that we have area which is given as 2.5 into 10 to the power minus 3 square millimeter, and first we'll find the maximum load P that can be applied. So from here you can see FAB is equal to P, FBC is 1.33 P, and FBD is 1.67. So maximum force is FBD, and that is equal to 1.6667 times P. And we have been given that A36 steel. So for A36 steel I will write E value and yield stress. So E we will check it in the property table. So you can see here that this is the A36 steel. So E is 200 gigapascal and yield strength is 250 megapascal. So we'll note down this. This is 200 gigapascal, which is 200 into 10 to the power 9 pascal, and yield strength is 250 megapascal, so 10 to the power 6 pascal. So yield strength, again the yield stress we will have maximum load. So let this is equal to FBD divided by area. So yield stress is 250 into 10 to the power 6, and FBD is 1.3. FBD is 1.667. 1.6667 times P divided by area is 2.5 into 10 to the power minus 3. So from here, when you calculate, you will get the P load that is applied on this truss. So when you get this P, clear, against the yield load, so you can just put it in this formula. You will get FAB, you will put P over here, you will get FBD, and you will put P over here, you will get FCB. So putting P is equal to 3.75 kilonewton. In above equations, you will get FAB is equal to 375 kilonewton, FBD will be equal to 625 kilonewton, and FBC will be equal to 500 kilonewton. So these are the axial forces in each member. Now we will also find we have length of CB, LBC or CB. This is length of AB. Clear? So length of this BD can be obtained by using Pythagoras theorem. So this length of BD will be equal to 2 square plus 1.5 square under the root, and that will be equal to 2.5 meter. So I will write it 2.5 meter. Now we will use this equation in order to find. So UI, strain energy due to axial loading, will be equal to sum of, so for FAB square into length AB divided by 2 times area, and E will be same because same material and same area is given, plus FBD square into LBD divided by 2AE plus FBC square into LBC divided by 2AE. And since the force in this member AD is 0, you can see we will not include it. So from here, if you take 1 over 2AE common, clear? So it will be equal to FAB square into LAB plus FBD square into LBD plus FBC square into LBC. Now just put the values 1 over 2 multiplied by 2.5 into 10 to the power minus 3 multiplied by E, which is 200 gigapascal. So 200 into 10 to the power 9. FAB is 375. So 375 into 10 to the power 3 square into length of AB. AB is given as length of AB is 1.5, length of BC is 2. So 1.5 plus FBD, which is 625. So 625 into 10 to the power 3 whole square into BD length. BD length is 2.5 meter. So I will write 2.5 plus FBC. So 500 into 10 to the power 3 square, and length of BC is 2. So again, this will give you strain energy due to axial loading. So when you solve this, you will get strain energy due to axial loading will be equal to 1687.5 joule, or that will be equal to 1.69 kilojoules. And this is the answer of our this question. And that was all about this problem 14-7. I hope you have enjoyed this video and you have learned from it. Those who are new to my channel, then subscribe it and don't forget to press the bell icon so that you can get notification about my latest videos. If you have any question, you can ask me in comment section. Thank you for watching. Welcome back. In this video, we are going to solve problem 14-8 that is taken from chapter number 14, Energy Methods, and book name is Mechanics of Material by R.C. Hibbeler. So statement is determine the torsional strain energy in A36 steel shaft. The shaft has diameter of 40 millimeter. So you can see this is the shaft. At this end, we have 300 Newton into meter torque. At this end, we have 200 Newton meter torque, that is counterclockwise. And here, this is at 900 Newton meter clockwise. The length of the shaft is given as 1.5 meter. So we have to find the torsional strain energy due to the applied torque. So let's start with the solution. So as we know that strain energy UI due to this torsional is equal to sum of T square into L divided by 2 times G into J, where T is torque, L is length, G is modulus of rigidity, and J is polar moment of inertia. So what we are going to do is that we will take this point A, this is point B, and this is point C, and this is point D. So we'll find in torque in various sections of this shaft A, B, B, C, and C, D. So let's start to find the for section AB. For section AB. So if you cut this at this point clear and draw the free body diagram, so the beam will, so the shaft will be like this. Clear. Here you can see that the torque applied here is counterclockwise in this direction, which is 300 Newton into meter, and this is the x-axis. So in order to balance it, we should have clockwise torque. This is clockwise torque, counterclockwise. So in order to this counter, we will be having a clockwise torque. So it will be like this, and this is point A. So we will have TAB. How we will find TAB? By applying this equation of equilibrium, that sum of all moment about x-axis must be equal to 0, and torque is taken counterclockwise is positive. So you can see this is clockwise torque, it will be negative, and this is counterclockwise torque, it is positive. The sum must be equal to 0. So I will write minus TAB plus 300 is equal to 0. So from here, you will get torque in shaft AB is equal to 300 Newton meter, and that is clockwise. Now what we will do is that we will cut this beam in section AB, BC. So I will write for section BC, here it was AB. So when you cut it and draw the free body diagram of this shaft, it will be like this. You can say this is point A, where you have a torque of 300 Newton into meter. Clear? This is your point B, where again you have counterclockwise torque of 200 Newton into meter, and this is the x-axis. So in order to balance it, we have a clockwise torque which will be equal to TBC. So the length from this till this, it is given as 0.5 meter, and this is also from B to A is 0.5 meter. So we'll find this torque by using sum of all moment about x-axis must be equal to 0 and taking the counterclockwise torque as positive. So TBC, which is clockwise, so I will write minus TBC plus 200 plus 300 is equal to 0. So what we will get is that TBC will be equal to 500 Newton into meter, and the TBC will be clockwise. Now we will section it at point C, between D and C, and if I draw the free body diagram, so it will be like this. This will be the shaft here. So you can see this is the axis. So at point A, again we have 300 Newton meter, that is counterclockwise. This is point B. So at point B, we again have 200 Newton into meter, and this is your point C. At C, we have clockwise movement of 900 Newton meter. So in section CD, the torque will be equal to TCD, and that be taken as clockwise. TCD is equal to we will find this TCD. So how you will find this? So you will take sum of all moment about x-axis is equal to 0 and taking the counterclockwise torque is positive. So minus TCD, which is taken as clockwise, plus minus TCD, which is clockwise. Again, you can see this is clockwise. This TCD is 900 is again, this is also clockwise. So I will write minus 900 plus 200 is counterclockwise plus 300 is also counterclockwise. Their sum must be equal to 0. So TCD will be equal to minus 400. So what does it mean? It means that assumed torque TCD, which is taken as clockwise, is wrong. It should be counterclockwise. So we will write TCD is equal to 400 Newton into meter, and it should be counterclockwise torque. Now we have torque in each section, so we will use this equation, and this equation is given as strain energy due to torsion is equal to sum of T square into L divided by 2GJ. So we have different sections, so I will split it TAB square into LAB divided by 2GJ, since the material is same and diameter is same. So TBC square plus TBC square into length of BC, LBC divided by 2GJ plus TCD square into LCD divided by 2GJ. Now, G can be obtained from the material property. We have been given as A36 steel. So we will go to the property table, and you can see that A36 steel. So G will be equal to 75 gigapascal. So we will note down it. So G is 75 gigapascal. That is equal to 75 into 10 to the power 9 pascal. And what is J? J is polar moment of inertia. And for radius, we have been given diameter. So radius C will be equal to D divided by 2, which is equal to 40 divided by 2. And that is 20 millimeter. And 20 millimeter is 0.02 meter. So J is pi by 2, C power 4. Since it is solid shaft, so you can put the value pi by 2, 0.02 power 4. Clear? And when you calculate it, you will get J will be equal to 80 into 10 to the power minus 9 pi. And unit will be meter power 4. Now you have all the values. You can just put it in this formula. So strain energy due to torsion will be equal to, first we will put TAB. So TAB is 300. So if you take 1 over 2G, J common. So this formula will become equal to TAB square into LAB plus TBC square into LBC plus TCD square into LCD. Now you can just put the value. So strain energy due to torsion will be equal to 1 over 2. G is 75 into 10 to the power 9, and J is 80 into 10 to the power minus 9 multiplied by pi. Clear? Okay, TAB is 300. So 300 square multiplied by length of AB is 0.5. Same length of BC is 0.5 and CD is 0.5. So we can put the value 0.5. TBC is 500 Newton into meter. So 500 square into 0.5 plus TCD is 400. So 400 square into 0.5. Okay. Now you have all the value. If you simplify it and solve it using calculator, so you will get strain energy due to torsion will comes out to be 6.63 joules. So this is the amount of strain energy due to torsion that will be stored in this shaft. And that was all about this problem 14-8. I hope you have enjoyed this video and you have learned from it. Those who are new to my channel, then subscribe it and don't forget to press the bell icon so that you can get notification about my latest videos. If you have any question, you can ask me in comment section. Also share my video with your friends and help me in growing my channel further. Thank you for watching. Welcome back. Problem 14-9. This problem is taken from chapter number 14, Energy Methods, and book name is Mechanics of Material by R.C. Hibbeler. So statement is determine the torsional strain energy in A36 steel shaft. The shaft has radius of 40 millimeter. So you can see this is the shaft. At this end, we have 8 kilonewton into meter torque, that is counterclockwise. At this end, we have 6 kilonewton into meter clockwise, and at this point, we have 12 kilonewton into meter torque. The length from this end to this is 0.6, and then between these two torque 0.4, and then at the end from this torque it is 0.5. So diameter of shaft is given here, which is 0.404 meter, and it is A36 steel shaft. So you have to determine the strain energy due to torsion. So let's start with the solution. So we know that strain energy due to torsion is equal to sum of T square into L divided by 2GJ, where T is torque, L is length, G is modulus of rigidity, and J is polar moment of inertia. So we will find the torque in each section. That this is point A, this is point B, this is point C, and this is your point D. So what we are going to find, we will find the torque in section AB first. So what if I cut this beam or this shaft over here and draw the free body diagram? So it will be like this. This is for section AB. So I will also write it for section AB. So you can see this is the axis here. So at this end we have counterclockwise torque, which is 8 kilonewton into meter. So in order to balance it, counterbalance it, so we will have a clockwise torque, which will be like this. Here, and this torque will be equal to TAB. So how we'll find this TAB? By using equation of equilibrium. This will be axis. Sum of all moment about x-axis will be equal to 0, or sum of all torque about x-axis will be equal to 0. Taking the counterclockwise torque as positive. So 8 kilonewton will be positive minus TAB will be negative. Their sum must be equal to 0. So TAB will be equal to 8 kilonewton into meter. This is the torque AB that will be generated in section AB. Now what we will do is that we will section it between B and C. So for section, I will write for section BC. So if I section it, so the beam will be like this. Clear? This will be the axis, this will be x-axis. Here at point A, you will be having a counterclockwise torque, which is 8 kilonewton into meter. This is your point B, where you have a clockwise torque, which is equal to 6 kilonewton into meter. And at point C, you will be having, that we will take this torque. You can see this is 8 kilometer counterclockwise, and this is 6, so net torque will be clockwise. This will be equal to TBC. So how you will find this TBC? By using equation. This will be equal to 0, so 8 kilonewton into meter is positive torque, minus 6 minus TBC will be equal to 0. So from here, TBC will be equal to 2 kilonewton into meter. This is the torque that will be generated in section BC. Now the final thing is that we will find the torque in section CD portion. So for that, we will cut it and we will draw the free body diagram of this shaft here. Again, this will be the axis. There, this is point A where you have counterclockwise torque 8 kilonewton into meter. This is your point B where you have a clockwise movement which is 6 kilonewton into meter. This is point C where you have again clockwise torque of 12 kilonewton into meter. So our net torque, which will be TCD, will be equal to counterclockwise. It will be counterclockwise TCD. Yeah. So how you find that? Again, you will apply this equation of equilibrium in order to find TCD. So 8 minus 6 minus 12 plus TCD is equal to 0. So 18 minus 8 is minus 10. So TCD is equal to 10 kilonewton into meter. Now you have all the torque. So what we are going to do, we'll use this equation. So this equation will become strain energy due to torsion will be equal to TAB square L over 2G LAB plus TBC square into LBC over 2GJ plus TCD square LCD divided by 2GJ. Since material is same and the diameter is same, so we will take out 1 over 2G as common. So this will become equal to T square AB into LAB plus T square BC over L into LBC plus T square CD into LCD. Now what is the value of G? We have been given A36 steel. Clear? So from mechanical property table, we will get the value of G. So we have to go to the book. At the end of book, there is every mechanical property table, and from here we can see A36 steel and the value is 75 gigapascal for this G. So I will write down 75 gigapascal, and that is equal to 75 into 10 to the power 9 Pascal. Now what is J? J is polar moment of inertia, and it is equal to pi by 2 C power 4, where C is radius. As we have been given diameter, which is 0.04 meter, so C will be equal to D divided by 2, and this C will be equal to 0.02 meter. So J will become equal to pi by 2, 0.02 power 4. Okay, this is the radius. So this is radius. So this will be 0.04. So again, radius is directly given. C is equal to 0.04, not 0.02. So this will be also 0.04. So now you can put the value over here. So strain energy due to torsion will be equal to 1 over 2 multiplied by 75 into 10 to the power 9 multiplied by J, which is pi by 2, 0.04 power 4 into TAB. So TAB is 8 kilonewton. So 8 kilonewton is 8,000 newton square into length of AB, which is 0.6. You can see this is 0.6, length of BC 0.4, and that is 0.5 for CD. Plus TABC, which is 2 kilonewton, which is 22,000 newton into meter. So 2,000 square multiplied by 0.4 plus TCD is 10 kilonewton, which is 10,000 newton into meter multiplied by length is 0.5. Okay. So when you solve this, you will get strain energy due to torsion comes out to be 149 joules. And this is the amount of energy that will be stored in this shaft due to this applied torque. And that was all about this problem 14-9. I hope you have enjoyed this video and you have learned from it. Those who are new to my channel, then subscribe it and don't forget to press the bell icon so that you can get notification about my latest videos. If you have any question, you can ask me in comment section. Thank you for watching and supporting me. Welcome back. In this video, we are going to solve problem 14-10 that is taken from chapter number 14, Energy Methods, and book name is Mechanics of Material by R.C. Hibbeler. So statement is the shaft assembly is fixed at C. The hollow segment BC has inner radius 20 mm and outer radius of 40 mm, while solid segment AB has a radius of 20 mm. Determine the torsional strain energy stored in the shaft. The shaft is made of 2040 T6 aluminum alloy. The coupling at B is rigid. So you can see this is shaft BC and this is shaft AB. The end C is fixed. There is a coupling between in shaft BC and AB, which is rigid. At point A, we have a clockwise torque of 30 Newton into meter. At coupling, we have 60 Newton into meter, clockwise torque of 60 Newton into meter. And this BC is hollow. Inner radius is given as 20 mm CI, and C outer for BC is 40 mm, while solid segment AB has radius 20 mm. So you have to determine the torsional strain energy stored in this shaft. So let's start with the solution. As we know that strain energy due to this torsion is equal to sum of T square into L divided by AB. Why this formula? Because you can see we have two different sections, so we will find this torque. So for this portion AB, this formula will become equal to UI due to torsional will be equal to TAB square into LAB divided by GJ. This is not AB, this is GJ. So GJ. So JAB. Material is same, only diameters are different. And this for segment BC, it will be TBC square into LBC divided by GJBC. Now, how will find torque AB? So we will cut this in segment AB. So I will write for segment AB. When you draw it, the free body diagram will be like this. Here you have, this is the axis, for example, x-axis. So at this is your point A. So here at A you have a clockwise torque of 30 Newton into meter. So in order to balance it, you have TAB is you will be having TAB. In order to find TAB, we will apply equation. Sum of all moment about x-axis must be equal to 0 and counterclockwise taken as positive. So torque TAB, which is counterclockwise, and the other one which is minus 30, their sum must be equal to 0. So it means that TAB is equal to 30 Newton into meter. So this is the torque in internal torque in this segment AB. Now we will apply for, we will find for the segment BC. For segment BC, I will cut it along any length of BC and draw the free body diagram. So it will be like this. This is BC. Clear? There is a coupling over here, and then we have another segment which is segment AB. Okay. At this point, this is point A, where you can see you have clockwise torque of 30 Newton into meter. This is coupling here at our point B. So at point B, we have a torque of 60 Newton into meter clockwise. So this is the axis. Clear? So the net torque will be equal to counterclockwise, and that will be TBC. So how you'll find this TBC? By using this equation of equilibrium. Now you apply TBC is counterclockwise, so it will be positive. Minus 60 minus 30 will be equal to 0. So from here TBC will be equal to 90 Newton into meter. Now you have TAB and TBC. Length of AB is given as 600 millimeter, which is equal to 0.6 meter. Here, 0.6 meter. Length of BC is also again 600 millimeter. That will be equal to 0.6 meter. G, we will find G by using mechanical property table. So for T, 2014 T6 aluminum alloy, we will find G. So G for this will be equal to, again, you will go to the property table. Again, we have to find this table. You can see this is the table. And here from this, T, 2014 T6. So G is 27 gigapascal. Clear? So note down it, 27 gigapascal. So G is 27 gigapascal. That is equal to 27 into 10 to the power 9 Pascal. Now what about JAB and JBC? So JAB is for solid segment. For solid segment, JAB is equal to pi by 2 CAB power 4. CAB is given as 20 millimeter. So in meter, it will be equal to pi by 2, 0.02 power 4. And that will give you 80 into 10 to the power minus 9 pi, and unit will be meter power 4. Okay, now for hollow segment BC, this JBC will be equal to pi by 2 C outer of AB, BC, not AB, BC power 4 minus C inner of BC power 4. Okay, so you can put the value pi by 2 C outer was 40 millimeter. Clear? Let me check it. That is C outer is 40 and C inner is 20. Okay, so 40 is 0.04 meter. Clear? Power 4 minus C inner was 20, and that 20 millimeter, which is 0.02 meter, power 4. That will be polar moment of inertia for this hollow segment BC. Again, when you solve this, you will get 1200 into 10 to the power minus 9 pi, and unit will be meter power 4. That will be JBC. When you have all these values, you can just put it in this formula. Clear? Which was strain energy due to torsion will be equal to TAB square into LAB divided by G JAB plus T square BC LBC divided by G JBC. So put the value TAB is 30 Newton meter. So 30 square into length is 0.6 divided by G is 27 gigapascal, and J is 80 into 10 to the power minus 9 times pi, plus TBC. TBC you can see 90. So 90 square multiplied by length is 0.6 divided by G is 27 into 10 to the power 9, and J is 1200 into 10 to the power minus 9 times pi. That will give you strain energy due to torsion. And when you solve this, you will get 0.06379 joules. Strain energy due to torsion will be equal to 0.0638 joule. So this is the amount of strain energy that will be stored in the shaft due to the light torque. And that was all about this problem 14-10. I hope you have enjoyed this video and you have learned from it. Those who are new to my channel, then subscribe it, and don't forget to press the bell icon so that you can get notification about my latest videos. If you have any question, you can ask me in comment section. Also share my videos with your friends and help me in growing my channel further. Thank you for watching.